All right, everyone, we are back and we are going to go through our second problem on our practice exam with an RLC circuit. So let's go ahead. We have an RLC circuit here. I'm trying to find my pen. Here we go. RLC circuit, same as our usual, basically, ODE systems. So second order ODE now in terms of I instead of some, position or angle or other value or et cetera, et cetera. So we can look at this system now and we can start to analyze it. So we can rewrite this. Remember, we're very used to mx double dot cx dot plus kx of this form equals some input. So we can kind of draw some parallels with these parameters here. One thing is just to make sure that we convert all of these into our appropriate units. So I'm going to go ahead and start to pull out our notebook, and I'm going to use our practice exam notebook here, our Ruth table, and all that good stuff. And I'm going to start to analyze the system, but I'm also going to start to make some definitions because I do want to be able to kind of play with this for a little bit. So I'm going to go ahead and say that, so we have our big L equals 0.2, our R equals 1.5, our big C is equal to 100 times 10 to the minus 6. So I'm going to draw this parallel here, and we're going to say, now remember, so our omega n is going to be equal to square root of k over m, right? So, but in this instance, our k is going to be the 1 over big C, k over m, which is going to be divided by L. So this is going to be our omega n. This is going to be, our omega n is here. This is going to be our, that's our omega n. Our zeta, I'm going to call it omega n1. I'm going to call it zeta 1. Is going to be equal to basically C, which is going to be R divided by 2 times square root of Km, or Mk, which is going to be 1 divided by big C times L. So that's going to be our zeta 1. So we are definitely overdamped. We have a high natural frequency. So this is definitely going to be a problematic system to deal with. So we have some values, and actually we can now use these expressions here. So I'm going to pull these. I'm going to be moving these around, and I would definitely suggest you all to do the same. So I'm going to say my sig 1, or my sigma 1, is going to be equal to my sigma function, and then I'm going to call it zeta 1, and then wn1. So that's my sigma 1, and then my omega function, actually my omega 1, omega function is going to be zeta 1, omega, or wn. Excellent. So I've got those values. So now I can start working essentially with this system. All right. So do we meet essentially the time specifications here? So let's go ahead. Let's work through these problems. So we have a rise time goal. We have settling time. We have an overshoot. So let's go ahead and calculate those. So my rise time, TR function, should be a function of zeta 1, omega 1. Our TS function should be zeta 1, and then wn1, and that's omega 1. So our TS, same thing, function of sigma. Our TR should be omega 1, yeah. And it should be the same thing as 4.6 divided by sigma 1. Good. And we can do that rise time. The rise time function too, this should also be equal to pi divided by omega n, or wn1. Very similar. Excellent. So we've got our values. I've got our functions, or we've got our functions. And actually, I'm going to redefine that. That's my, that's my TP function. My rise time, though, actually, we can look at it real quickly here. just want to go back through our rise time. Rise time, ooh, that's wrong. Our rise time should be 1.8 over omega n. So our rise time, oh shit, I'm gonna fix that in the notebook. Should be equal to 0.8 divided by. Ooh. So let's go ahead and let's go back here. 1.8 divided by this. Yeah, so our rise time is very small. So this is actually a little incorrect. I need to get rid of this guy. TR is going to be n underscore equals to 0.8 divided by omega n. There we go. So now we got our values. We can kind of see and work in between them. So let's go ahead and look at this value here. So let's go ahead. So we've got, let's go ahead and rewrite this one. That's our TR function. This is TR function. Wn1. Good. Should match that value here. So if we're looking at our system, let's go back. So we're looking at our system here. Our rise time, let's see. Rise time should be less than 1 millisecond. So 1 millisecond is 1 times 10 minus 3 to the minus 3. Let's look at this numerically. So no, we're not less than that, so we're greater than that. Settling time must be less than 10 seconds. So our TS is good, so we're okay there. So we're fine on the settling time, we failed the rise time, and the overshoot must be less than that. So our MP function, zeta 1, overshoot must be less than this. Unfortunately, it's not because it's 94%. So we failed on zeta, and we also failed on our rise time. But we passed in terms of our TS function. So we don't meet the specification. So now we need to tune it, and we need to find essentially what those specifications are going to be. So this is our TS goal is going to be equal to, let's see, or actually TR goal. Actually, let's do TS goal. TS goal equals 10. So now we need to solve TS goal, set it equal to TS function omega. And we can see that it's going to be our TS goal is going to be a function of, I'm actually going to do it 4.6 sig 1. So we need our sigma to be basically, and actually we can even do this. We can make it a little bit simple. Reduce. So it needs to be less than 0.46. So those are our bounds. We should be a rise time less than that. So let's go. TS goal. Yeah, I think, why is that TS? Something's looking a little bit odd here. Oh yeah, it has to be flipped the other way, excuse me. So yeah, we need our sig1 to be greater than 0.46. So I'm going to stop. I'm not going to do that. That's a little bit harder to see. So we need this sig1 to be greater than this value here. And if we look at what is our sigma 1, let's go ahead. Sigma 1. We are indeed, so we're good. So we've hit that. Again, makes sense because we were fine on that regime. So now let's go a little bit further. So we also need our TR goal. And actually our TR goal equals 1 times 10 to minus 3. So that's our TR goal. Our rise time TR is a function of omega n, but it's also a function, actually, yeah, it's 1 over omega n. So let's go ahead and solve TR goal. Set it equal to 1.8 divided by omega n. So our omega n has to be larger than this in order to hit that goal. So quite large. We need high frequency essentially for that system. And then finally, we need to have our overshoot goal. So we need to have our value here. So our overshoot goal equals less than 0.64. And then we're going to say solve when overshoot goal set equals to MP function, and then whatever that zeta is. So our zeta has to be, again, basically larger than that value there. So we've got some bounds. So now let's go ahead and plot. We can actually go directly and we can plot the allowable pole region here. So let's go ahead and do that. But in order to do that, we need to actually have the poles of our system as well. So let's go ahead and let's set up our system up here. And we'll go ahead and set those values. So our system, our P of S, is going to be equal to the following. So equals L plus R plus 1 divided by big C. So those are our system. These are going to be the poles. And now we need to find our allowable pole region. So our allowable pole region initially, so we want something where the sigma, and let's go ahead and look at the function here. We need to do, actually sigma is the second. Our zeta goes first, or zeta. So we need something like this here. We need something like sigma here. And then unfortunately, we need that huge value here. So let's go ahead. We need the omega n. Now, is the omega n the value here? No, it's not. Yes, we do actually. So we actually have it directly. So that was very nice. So we can go ahead. We're going to have to actually plot. So allowable pole region. Let's see what we've got here. We are way off because our sigma there is fine. Our omega n is huge. So we may need to change essentially the plot range here. You can say, actually, it'd be nice to put the plot range all. There we go. So you can visualize and essentially see that system. So obviously we're way off. So we fail essentially the system, and we can actually see where we're failing it. So we need to essentially raise that omega n up. We need to fall within that region. We're also kind of far away from this value here. So we see those two regions where we fail. So how do we actually make essentially these values? Because remember, our zeta 1 is also very, very, very bad. So we need to solve essentially these values. So we need to do two things simultaneously. So I need to solve, when will my zeta, and remember zeta is equal to, so let's look at our zeta function here. In general, it is going to be, let's go ahead and look through our system here. Our zeta function, where are we looking at? So let's go ahead. Let's look for these values here. We'll make sure. So our zeta, let's just set this general, just like we did over here. So this is our zeta. I'm going to pull this in over here. I'm going to say, I'm going to call everything new. Oops, not renewal process, just renew. R new. 1 over big C new. 1 over L new. Good. So that's our zeta. We also know that we failed the omega n as well, so we can pull that value. So we can pull this value here. So we have multiple equations that we need to satisfy this. We also say this has to be equal to or greater than this. So we can specify that right there. So I'm going to call this again new. And then finally, we have basically 4.6 over sig. So we have sigma must be equal to this, but we also know that sigma is equal to zeta omega n. So we can say our zeta, which is this. Now, interestingly, we can actually simplify this a little bit here. Zeta times, actually, let's see if we can full simplify. Yeah, it's okay. So this will be, we can set also this. So this equals 0.46 or whatever that one was. Yeah, 0.46. So 0.46. So now we have these three conditions. We have three equations. We have three unknowns. So if we wanted to, we can actually just solve for now. What I was thinking about previously is like, okay, well, if we just want to change this and this, and we don't want to influence essentially these other values, but they're all a function. So, so let's actually see. So let's keep, I would propose the following. Let's keep L constant. What if we keep L constant? Can we satisfy this expression or these expressions and not change this? Looks like we got some values here, but oops, we still need L if we're keeping L constant. Ooh, interesting. So let's see. What if we keep L new? We just kept this as R. This would put us right on. Let's get rid of. Let's just look at here now. Let's see here. If we just keep R, we're going to change this. So now we have some values here. So let's see what happens to the system if we just went and changed this. So let's call, so this is the old system. Let's choose the new system here. So what if we change these values? So now big C new is this, and L new is this. Oof, right on it. So let's see. Let's see how far we can tune this. So for example, let's change this to 9. I'm just increasing the values here. 9, 9. Oops, that's a little bit too far. Let's change this. Because it changes this here. Big C new is this. 229 was this. So this puts us just on the border. So we would just put us on essentially those regions. If we wanted to make this even smaller, so I think we would need the values to be slightly greater. So let's just put 2 here. But they are interrelated. That's the problem. Yeah, so I need it less than. 103. How about, let's change this to 1. Excellent. So you can see essentially we can push them into this region. Actually, let's just do 0, 5. Because I want to push it to the left. Ooh, that's a little bit dangerous. So one of the things I could do, I can also change R. Ooh, there we go. We see this. We're drifting away now. We're not looking okay. But I can put this on here, and that would allow me to do the pull region. Alternatively, I could also try to shift over here and put my system in that position. But for right now, I think that we're okay. I think that we fit essentially in that region, and we hit essentially that allowable pull region. So, but yeah. But let's see what would happen actually. Let's, just for curiosity's sake, let's not change R. So let's say R new, and let's keep L constant. So now we can say, all right, so let's increase R. So R currently is what? Probably 100. So let's go ahead. We'll just do this now. Put this here. And then we can put this as our L, and then our R new would be this. We can just look. I'm just looking what the system looks like. Again, we're right on the region here. But if I push this into 2, that's going to be 2. That's going to be crazy. Ooh. Maybe if I do 2,000. Nope, I get 2. So again, you can tune this. This is actually a pretty hard one to tune in this instance. But yeah, you can see we can push this maybe a little bit. We're kind of like on those this value here. What if we go to the -7? I think this will freak out. Order of magnitude changes are always tough. Yeah. So -6 here. Let's go -6, but let's do this 2. Because we're raising ourselves up just a little bit. Ooh. How about let's make it 0. Yeah, we can tune the parameters, and maybe we can go a little bit. Let's go like 300. There we go. So this is a nice, I actually really, really like this. We're nice and safe in the pole region, so fantastic. Multiple ways to solve this answer. Excellent. So do we meet time specifications? Nope. We proved it. Do we tune the physical system? We plotted the domain. Which system properties will create a circle feature in the domain specification plot? Ooh, excellent question. So remember from our domain, we were looking at here, this is our omega n. So omega n effectively controls essentially the radius of that circle, or the value there. Fantastic. Yeah, that's pretty much it. So we'll see you all next time in your third problem. Maybe it's fun just to kind of look at, okay, well, what does this system look like? And is it indeed stable? But I think we definitely know that. But we can go ahead and say, okay, my R of S, or actually my U of S is equal to Laplace transform of 3TS. So U of S, so I can do my PS times US. I can do inverse Laplace transform. And we can do S to T, and I can say this is my YT, and I can say plot YT, T from 0 to 10. Ooh, it's a very fast response, but it's because of my parameters mostly. So I can actually go from 0 to 1, actually even less, probably I need to go from 0 to because what were our time domain specifications? So we didn't want that overshoot. So you can actually verify, so maybe 3 times 10 to the -3. Because we said that our settling time needs to be less, so we can kind of see that rise time. Let's go ahead, let's do 30. Plot range all. So yeah, we can see essentially what was our settling time at the end of the day now with these new features. So you can recalculate, you can confirm it, but you can kind of see that's a fast rise time. And actually, you can just recalculate it. And actually, I should actually show that that is indeed the case. That now, what is my omega n? What is my? Actually, we can do that quickly here. So I can say my new zeta, new zeta equals, and I can say, okay, I'm going to do this new zeta equals c, which is this, divided by 2 times square root of m times k, which is this feature here. New zeta, new omega n equals square root of k divided by m, which is just L. So we can see here 3,000. So we already beat, or actually we know that we have that, but we can just look at the time domain specifications here. So I can say, and we can pull it up. So here, I'm going to pull this one over here again. So I'm going to say my TR function, which should be a function of new omega, our omega function, which is zeta, new omega n. So are we less than that millisecond? Yep, we are indeed. The settling time has to still be less than that, but I think we're still okay, but let's check. TS function. TS is a function of just new zeta and omega n. And we are definitely really, really good there. And you can see the settling time looks to be about correct too. Fantastic. And then finally, our MP function, which is just new zeta. We can see 43%, fantastic. And look at that, we're probably not that far off. We can probably calculate that. Excellent. So that is pretty much it. So we'll see you all in the next video. Thanks. Bye.